Today we're talking about section 12.1, which is our introduction to sequences. This is the first section of chapter 12. Chapter 12 deals with what we call sequences and series. Today is going to be specifically sequences. We'll get into series in 12.2. As we start to talk about sequences, there's obviously some initial vocabulary stuff we need to deal with, and then we'll get into how do we actually use these things, how do we find some terms of the sequence, and then how do we write rules for a given sequence as well. So, I've said sequence a lot of times. We should probably talk about what a sequence is. A sequence is, in the simplest form, an ordered list. Actually, I'm going to call it an ordered set of numbers. So it's really just a set of numbers that have an order to them. You can also think of this as a list of numbers with a pen. Okay, and I hesitate to say because sometimes that pattern is either really defined or there's not really a pattern, and that kind of is the pattern that's there is the fact that there isn't one, which can get a little confusing, but we'll talk about that more a little bit later. When we start to talk about our sequences, we're also going to talk a lot about terms. So we have the term of a sequence, which is simply each individual number. So each number in the sequence is what we call a term. Okay, so just kind of each number in the list is called a term. Each term is also given a number, which gets a little bit weird because we just the term and now the term gets a number. The term number is basically the position that it's in. So this is the position of a number in the list. Okay, an easiest way for me to explain this was to actually give you an example. So if I talk about the third term, so I have a list that has a bunch of numbers, but the third number in the list is the third term. That third term, the term number, is simply 3. So it's the number kind of position that it's in. So I have the first term, the term number is 1. Second term, the term number is 2. Third term number is 3, and kind of so on. This starts to get us into what we call infinite sequences versus finite sequences. Infinite sequences, infinite kind of refers to infinity, which means that this sequence does not end. So sequence does not end, meaning that it goes on forever. Okay, I can give you an example of that. Best example is probably our whole numbers. If you just start counting whole numbers, adding 1 every time, you're going to be able to count forever. Okay, there is no end to that list. Okay, but we also have things called finite sequences. Okay, finite sequences are basically the opposite. They do end. So we say these are sequences with a limited number of terms. Okay, so for an example, okay, I can still use my whole numbers, but we're going to make it a list. So I'm going to create my kind of set notation, my bracket there. I might have 1, 2, 3, 4, and 5, but then it stops. Okay, if I go back to infinite sequences, I can list the exact same sequence. 1, 2, 3, 4, 5, but the way I indicate that it goes on forever is I put another comma and I put 3 dots at the end. Those 3 dots at the end just kind of indicate that it keeps going and it's going to continue to follow that same pattern. Next thing we need to talk about is kind of the notation that comes along with sequences. This is probably the hardest part of this, is just understanding the notation and what we're actually talking about. When we start to work with sequences, we're not going to use function notation anymore. Function notation was the f of x, kind of using x's and y's and that f of x piece to indicate the patterns and whatnot. Now we're going to start to use subscripts. What I mean by subscripts is they're kind of like exponents, but they're down below. So if you look here, there's an example of one right here. This is what we call a sub 1. Okay, a sub meaning subscript 1. This indicates the first term. So the subscript is actually the term number. So when I say a sub 1, that's the first term. If I want the second term, I change the 1 to a 2, so that's over here, a sub 2. And then I have what we call the nth term. Now the nth term, that n is like a variable. I don't know exactly what term it is. It's just kind of a general, it's some term in the list. So we use the n here, and I write it as a sub n, and I get that n down below. I know it's a little hard to see on the screen, but if you have it printed out, you can see that. So it's an a with a little n below it. Now, because that sequence kind of continues on and on, this does have to be a function. I can only have one number for each term that I have. I can't have two different second terms. Whatever the second number is, it's that number. I can't have two different options there. Excuse me. So for each number n, which is that term number, let's actually put that here. This is term number. It has only one value associated with it, and it's a sub n. Okay, and I just said this little piece here. We read this as a sub n. We always say sub and then whatever's down below. So this is a sub n, and that's going to be the term value that goes with it. So a sub n is the term value. N is simply the term number. Okay, so it's the position where this is the actual number that sits in that position. Okay, and that starts to get a little confusing because we're going to use those in different ways and different types of formulas as we start to go. The one note that I want you to very much focus on for this entire section is the note that I put here, kind of in italics. It says anything written in subscript is notation and does not impact the term values or the sequence. So any that I have down below here, 1, the 2s, anything like that, is just to indicate what term we're talking about. It does not change term values at all. It doesn't change anything along those lines. It is simply notation. Same thing as using an X or a Y or switching them to an M and an N. Those are just notation switches. Okay, and so they mean different things, but that is all just notation. It doesn't change the values at all. So let's actually start to get into some of these. The first thing we need to talk about are our two types of formulas. So we have two types of formulas that we're going to be using. They're what we call recursive formulas and explicit formulas. Those two formula types are going to be very important to kind of distinguish because they kind of tell you how to do them based on which formula you're given. So we're going to start with recursive, figure out that one, and we'll get to explicit in just a little bit. So start with like I said, recursive formulas are a little bit weird. They're going to be a rule, or basically a way to figure out the terms of the sequence, in which one or probably more previous are used to find next term. So I have to know a previous term in order to find the next term. Now that's really because what that means is if I want to say the 50th number list, I would have to know all 49 things before. End up being a lot, and so that's where the other formula comes that a little easier. Let's talk about our first example here. Actually, sorry, real quick. I want this one, a sub n minus 1. Okay, something that you're saying very often with the recursive formula. This a sub n minus 1 means that if I'm trying to find a sub n, so I'm trying to find a term, a minus 1 is the term before it. What we're gonna call this is the previous term. And whenever we're talking about a recursive formula, I need to see something like this. It might be a sub n minus 2, which means I go back 2 terms instead of just 1 term. But I have to have something along those lines. The other really important thing is that this a sub n minus 1 is just notation. The n minus 1, specifically the minus 1, does not change the value of the terms. All it does is tells us that we're using this term. So as I move this up here for example 1, our directions are to find the first 5 terms of the sequence with the given information. So I'm given this kind of bracket here, and this is a recursive formula. This is what we want our recursive formulas to look like. I give you a first term, so I have a sub 1, that's my first term, which is actually part of my answer already because I want the first 5 terms. First term is right there. So I'm going to actually just copy that over. A sub 1 is equal to negative 2. And then I need to find the other 4 terms that make up the first 5. So I need to then try and find a sub 2. Well, a sub 2 is going to be a little bit harder to find. I'm not just given it. So this is where I need to start to use a sub n. Well, if I'm solving or trying to find a sub 2, the 2 is in the place of the n. So what that means is that as I start to set this up, the 3 is there. I have a sub n again. N is 2, so this is a sub 2 minus 1 plus a 2 at the end. Well, if I just look at what I have here, 2 minus 1 is all in the notation there. I can do that real quick. 2 minus 1 is just 1. So this means this is 3 times a sub 1 plus 2. Well, a sub 1 is the first term that I already know. That's the negative 2. So I'm going to take that and plug that in. This is going to be 3 times a negative 2 plus 2. If I can do that, I'll have my second term. So if I just quickly kind of work through this, I've got to follow order of operations to do your multiplication first. Negative 2 times 3 is negative 6. Plus a 2 is going to give me a negative 4. So my second term here is the negative 4. Now, this notation that I went through at the beginning here is just to kind of explain what we did. I do not have to show that first line that I put here. I really just need to see that I'm plugging in the previous term, which I can see is that a sub n minus 1. This piece here is that previous term piece that I was talking about right above this, which is why I'm plugging in that negative 2. But we can see the notation works out to do that as well. So if I go ahead and go for a sub 3, now I need to use the previous term to a sub 3. So this is going to be 3 times, well, the previous term to 3 is 2, which my answer was a negative 4. So I plug in the negative 4, and I add 2. Well, 3 times negative 4 is negative 12, plus 2 gives me negative 10. And I keep going. I need to find the first 5, so I need to find a sub 4 and a sub 5 yet. Well, a sub 4 is going to be 3 times the term previous to it, which is a sub 3, which was negative 10. And then I'm going to add in my 2. Well, 3 times a negative 10 is negative 30, plus 2 is going to give me a negative 28. And then finally, a sub 5, I need to plug that in as well. If I plug that in, that's 3 times a negative 28 plus 2. Well, 3 times negative 28 is negative 84. Yep, I'm just double checking that. Negative 84 plus 2 gives me a final answer of negative 82. Okay, so now I have all of my answers here, but I do want to kind of combine them together. I want to write this as a sequence. Now, a sequence is just a list of numbers, and it's separated by commas. So what I need to do is just list out my numbers in order. So I start with my first one, it's negative. Then I put a comma. Second one is negative 4. Third one is negative 10. Fourth is 28. And finally, negative 82. Okay, I'm going to go ahead and circle that. That is my final answer. Okay, and just a quick note, this really is how much work I should be showing here as well for each of these problems. Okay, let's go ahead and move on to part B. Similar type question, but just a different numbers kind of here. So I have a sub 1 is equal to 5, and a sub n is equal to 5 times a sub n minus 1. So again, this a sub n minus 1 is the previous term. So I'm going to start with my first term here. A sub 1 is still 5. But now I can go for a sub 2. A sub 2 is going to be based on a sub n, which is 5 times my previous term. Well, 5 times my previous term, my previous 5. So this is 5, which is 25. Then I go for a sub 3. Well, a sub 3 is going to be 5 times my previous term, which was 25. 5 times my 25 is going to be 125. And we go again. A sub 4 is going to be 5 times the previous term, which is 125. 5 times 125, you might need your calculator for that one, should be 625. And finally, a sub 5 is going to be 5 times 625. Probably need to grab a calculator for that one. I already have my answer here, is 3,125. So I now have all my answers again. I want to list those out. 5, 25, 125, 625, and 3125. Hey, it is a nice habit to get into to just list these numbers out, because you can also just make sure you found enough of them. I've asked you for the first 5 terms here, so I have 5 answers. I know that I'm done. Alright, next piece here, let's talk about example 2. Example 2, if you look at the directions, they're the exact same. It says find the first 5 terms of the sequence given the following information. But if I look at what I'm given, it's quite different. Okay, I don't have a first term. I don't have a sub 1. all I'm given is this a sub n is equal to 3 to the power of n minus 1. The other thing here is this n is in the exponent. It's not a subscript. So now that is part of the formula. I'm going to have to plug something in there, and that's going to change some numbers around. So let's start to figure this out. If I want to find my first term, a sub 1, I'm taking and choosing my n value to be 1. Okay, and that's on a subscript of a. But that n is the same n that's a part of the formula. So if I choose this to be a sub 1, I need to plug 1 in for n. When I do that, I have 3 to the power of 1 minus 1. Well, 3 to the first is just 3. 3 minus 1 is 2. That's the first term. So now I need to find second term. Well, second term is a sub 2. So I'm taking the 2 and I plug it in for n. Now, just a quick note here. This 2 that I'm plugging in for n is because I'm finding my second term. It's not because I had 2 for an answer in the first term. Okay, I know that looks kind of like that recursive piece if I'm plugging that answer in, but as we go, you're going to see that I don't use this answer anymore. I'm using the term number from that subscript. So when I plug this in, this is 3 to the second minus 1. 3 to the second is 9 minus 1 gives me 8. Next one is going to be a sub 3. Here's where you're going to really see this. I'm not going to use the 8. I'm going to plug the 3 in for n because that's the value that I'm using for a sub n. So this is going to be 3 to the third. Well, 3 to the third is 27. Minus 1 gives me 26. Next one, I'm going to do a sub 4, which is going to be plugging in the 4. So 3 to the fourth minus 1. 3 to the fourth is 81. Minus 1 gives me 80. And finally, a sub 5. Plugging in the 5 for that power on the 3, minus 1. 3 to the fifth is 243, minus 1 gives me 242. Okay, now I'm doing a lot of those. I've already have my answer key here, so I'm using that. You may need to grab a calculator to work through some of these. Okay, and any old calculator will work. Doesn't have to be anything fancy for these ones. Should write my answer out here though. So 2 times 8, 26, 80, and 242. Sorry, give me your last answer. 242. Okay, and finally, let's talk about part B here. Same idea. I'm taking my a sub n, and I need to plug in my values of n. Now, this one's a little bit different because I actually have 2 places where I'm plugging in the n. I still have to plug in that same number. So if I'm trying to find a sub 1, I need to plug in 1 both places where I see n. So this is going to be 1 squared minus 2 times 1. Well, 1 squared is just 1. 2 times a negative 1 is 2, or negative 2 times 1 is negative 2. 1 minus 2 is a negative 1. And if you need to show some more work for that, that's fine. I'm trying to keep this video as short as possible. I know it's already starting to get pretty long. A sub 2, I'm going to plug in a 2. So I'm going to plug in 2 squared minus 2 times 2. Well, 2 squared is 4. 2 times 2 is also 4. 4 minus 4 is 0. And we'll go to the next one. A sub 3 is going to be 3 squared minus 2 times 3. Well, 3 squared is 9. 2 times 3 is 6. 6 minus 9 is 9. A sub 4 is going to be 4 squared minus 2 times 4. Well, 4 squared is 16. 2 times 4 is 8. 16 minus 8 is 8. Last one ran out of room on the bottom, so I'll move up to the side here. A sub 5. It's going to be 5 squared minus 2 times 5. Well, 5 squared is 25. 2 times 5 is 10. 25 minus 10 is 15. Write your answers out here. Negative 1, 0, 3, 8, and 15. Okay. So, what we just did in example 2 was actually our second type of formula here. So let's just be real clear here. Recursive formulas, this is example 1. Okay, example 2 is going to be what we called explicit formulas. Okay, so this is on to the next page here. Example 2 is explicit formulas. Okay, explicit formulas are a little bit different. They are defined, or defines, the nth term, so some term of the sequence, as a function of n. Okay, what that really means is it means that I'm now going to be able to find terms without knowing the previous terms. So we do not need previous terms, which is important because now if I ask you that question that I asked back on the front side, oops, sorry, you couldn't see a bunch of that. What I asked on the front side was, what if we need to find the 50th term? Well, with an explicit formula, you just plug in 50 and you have your answer. It's pretty straightforward. The recursive formula, you had to find all 49 terms before that. So the amount of work that goes into each one can vary quite a bit, just given the information that you have to start with. And so there is kind of advantages to both. If you're finding terms, the explicit form is probably easier. But what we're going to move into now is writing sequences, or rules for sequences. So if I give you a list, how do we create the equation that goes with it? That's usually easier to actually do the recursive. So that's kind of the benefit of recursive, is that tends to actually be a little easier. So as we get into this, just a quick note, make sure that your sequence works for the given term numbers and corresponding terms. Just something that we need to check, make sure that first term matches up as we go through. As we start to talk about our explicit rules or explicit formulas, we're going to be using two patterns, what we call linear and exponential. These are patterns we've talked about already this year. The only difference is we're going to take our equations that we had, which were based on y's and x's, and we're going to change them to n's and a sub n's. So n is going to take the place of x, and a sub n is going to take the place of y. Now, as we start to do this, linear patterns are those constant differences. So we're talking about adding and subtracting patterns. Exponential patterns are based on multiplication and division. So if I have either of those patterns, I can kind of use the formula that corresponds with it. Okay, our formulas here, let's just quickly talk about these. Y equals mx plus b is for linear. M here is what we refer to as slope, but we're going to call it our change here. It's how much we're changing by each time, basically what we're adding or subtracting. B is going to be what we call our starting value. Start value. Okay, and we're going to have the same things for our a's and b's in a times b to the power of x. A, though, is going to be your start value. And b is your change. Okay, and we'll see how that works as we get into our first couple of examples here. All right, so first thing we should do here is we should start to try and identify what our pattern is. So if I look at example 3, I'm trying to write a possible explicit rule for the nth term of each sequence. So I need to find a sub n. To do that here, I have 5, 10, 20, 40, and 80. Hopefully looking at those, you can start to figure out the pattern. I am actually multiplying here. I am multiplying by 2 all the way through. And I would multiply by 2 to kind of keep going. Now, what that does is it tells me I'm multiplying, so I am going to use the exponential type equation. And when I do that, I'm using y is equal to a times b to the power of x. Okay, change is usually the easiest thing, so we'll start with that. I know I'm going to have a 2 to the power of x. Now, the start here is what's going to be a little bit weird. This x is where I'm going to plug in my term number. So when I plug in 1, I need to get my first term, which is 5. The problem is if I plug in 1, it's going to multiply by 2. So if I put a 5 here and I plug in a 1, I'm going to actually get 10 for my first term. And I'm off by 1. And so what I need to do is I actually need to go back one more to figure out what is the 0 term. What's not the first term, but what did we really start with before we even started to see our sequence? Well, to do that, I need to follow the pattern, but I need to do the opposite. So here I'm multiplying by 2. The opposite is to divide by 2. So if I take 5 and divide it by 2, it's 2.5, or I'm going to keep it as the fraction of 5 over 2. So this here is my equation, 5 over 2 times 2 to the power of x. And if I just want to quickly check that, if I plug in a 1, 1 times 2 is 2, or 2 to the power of 1 is 2. Then multiplied by 5 over 2, the 2's cancel, and I get 5. I get the first term. And I can check the second term real quick. 2 times, or 2 to the power of 2 is 4. 4 times 5 over 2 is 4 times 2.5 would give me 10. So that one is going to work out for us. The only thing I need to do here is, again, switch my notation. So I need to be going to a sub n and n. So my y changes to an a sub n. Then I have my 5 over 2 times 2 to the power of n. That n takes the place of x. Once I have that, that is my explicit rule. Okay, let's try out a couple more so that we can get into maybe some of those linear patterns. So I do have some decimals here. Doesn't matter, I can still figure out what my pattern is. I have 1.5 to 4 to 6.5 to 9 to 1.5. What I notice is that I go from a decimal to a whole number decimal, whole number decimal. So I'm probably adding something. If I look there, I'm adding, looks to be about 2.5, 2.5, 2.5. So I am adding 2.5 each time. And that kind of continues all the way through that list. So if I'm adding, that means this is going to be linear. And I'm using the equation y is equal to mx plus b. Okay, again, I'm going to start with the change. The change is the m in this case, which is how much we're adding each time. Here's 2.5. So I'm going to use 2.5x. Plus, I need to figure out my starting value. Well, starting value, again, is going to be just a little bit of an issue because I don't want to use 1.5. I want to plug in what was really the zero term. So I need to go back one more. To go back one more, I'm going to subtract 2.5. Well, 1.5 minus 2.5 leaves me with a negative 1. So I'm going to add a negative 1 in there for b. And I can switch that just to a minus 1 here in a second. Okay? And it's easy to do that when I switch notations. Again, I'm going to switch the y to an a sub n, which is an equal 2.5 times n minus 1. And there's my answer. Right, so you can see writing explicit forms is not necessarily the easiest thing, but it is really just based on that pattern. If you can find the pattern and come back to your notes here, that really should help you out. Okay, last one here, I have 7, 5, 3, 1, and then a negative 1. I threw this one in here just because of that negative 1 at the end sometimes throws people, but if I look, it still just follows the pattern. I'm going down by 2 every time. So I'm subtracting 2 all the way through. It does get me then into the negatives, and it would keep going more negative after that as well. Okay, if I continue that, that's an adding and subtracting pattern, so that's going to be linear again, y equals mx plus b. Now my pattern here, or my change, is the fact that I'm going down by 2, so I need to make my m a negative 2 with the x there to make sure that it goes down. Then I need b as my starting value, or that 0 term, so I'm going to go back. Now because of the opposite, I'm not subtracting 2 anymore, I'm going to add 2 to go backwards. Adding 2 to 7 gives me a 9. I'm going to add 9 there. Once I do that, I have everything set up. I can just switch notations. A sub n is equal to a negative 2n plus 9. Okay. All right, so that's our explicit rules. Hopefully that makes sense. Let's go ahead and move down to recursive rules and get this video finished up. So recursive rules are based on two things. We need the first term, and we need the pattern for the formula for the next term based on the first term. So the way we're going to set these up, and just bring the first page back over here, it's going to look like A and B. So what I need to do here is I need to start with my bracket. Okay, and I'm going to start with A sub 1, and I'm going to start with A sub n. A sub 1 is my first term. So if I look at A here, my first term is 5. Okay, now A sub n can be a little bit tricky. This is where we start to have to write the formula. The question I want you to ask yourself is, what do we do to the first number to get to the second? Well, that's really identifying the pattern. If you look here, A and B are actually the same A and B we used up here. So the pattern is still the same. I'm multiplying by 2. So I'm taking each of my terms and I'm multiplying the previous term by 2 to get to the next. So what that means is I need to take 2 and I need to multiply it by the previous term. Well, if we go back to what we said on the front side here, I told you how to write the previous term. It's A sub n minus 1. So we're going to take and plug in an A sub n minus 1 there. And I tend to put these in parentheses just to keep that A sub n minus 1 together. But you're more than welcome to just write it as A sub n minus 1. And if I look at my directions here, kind of what I told you, I need to give the formula for A sub n based on that previous term of A sub n minus 1. So you have to include an A sub n minus 1 somewhere in that formula. Okay, so there's my recursive rule. Let's do the same thing for B. Now this one's a little bit different because I knew this was a linear pattern, and I'm adding 2.5 each time. So I know I'm adding 2.5, add 2.5, kind of all the way through. Not that I take the time to write that. But if I continue here, I need my first term and my A sub n term. So my first term is going to be the first term in my list, which is 1.5. And then I need to follow my pattern. Well, here I'm taking my previous term and I'm adding 2.5 to it. So I'm going to start with my previous term this time. Okay, again, you could add parentheses around that if you want. And I need to take and add 2.5 to that. Okay, now this is really important. Make sure that a sub n minus 1 is part of the notation, so we don't confuse that -1 to be part of this formula. Okay, once we do that, if you want to, again, throw that in parentheses, you can. It's up to you, but that is your answer. So those two are your final answers. That does it for our notes for today. Hopefully that helps you clear up some of our sequences.